Alrighty, guys, can you hear me? Okay, so yesterday there were lots of questions about the homework in the office hours, and I decided that we're going to spend some time today going through the homework. There was some questions. There's one question in particular where it was Aya that pointed out that the way that the question is formulated is not really what I had in mind. So I also want to highlight that. You can answer the question the way that it is asked, but this was not what I had in mind. And I want to go through the construction that I had in mind. But there were many questions about the homework yesterday, and that's great. Some of you asked if I could post the videos from the office hours, and I'm not going to do that. I think the office hours should be spent very informal, just to have discussions. Instead, I would rather spend class time like this, trying to go over these issues that came up in homework. So I'm going to spend quite some time today going through some of the homework questions that you guys handed in last night. And I'm going to do it backwards. I'm going to start with problem number 2. So homework 8, number 2. And of course, you guys just interrupt me when I'm saying something that you disagree with. So the first question is, you go from R into R square. And so now it's 2-dimensional. So f of x can therefore be written as a vector. So cosine of x and then sine of x. And this is going to take, for a given x in R, this is going to be something in R2. But it's not going to be everything. This function is not onto. If it's not onto, because I cannot find f of x is not going to be equal to 7 for all x. Right, so that's not going to work. So if it's not onto, right, so the range of f, right, so the range of f, this is defined to be f applied to R. Right, this is a strict subset of R2. And in this case, the range of f is going to be the unit circle. Right, the range of f, this is going to be exactly those points. Let's call them y's in R2, such that the length of y is 1. But remember how we measure length in 2 dimensions is by taking the first coordinate and squared, taking the second coordinate and squared, and then you take the square root. Right, so the range does not include a point like 7/7. It's the unit ball. And it's the perimeter of the unit ball. That's the range, and it's also, so it's not onto, and it's not 1-to-1. It's not on 1, like you can take f at 0 is equal to f at 2 pi. Right, that's this point here, which is what's going to be the big troublemaker, is that point there. Right, are we good so far? So one thing that came up yesterday was, well, you have a function of 2 variables. How do you prove that it's continuous? So what I had in mind was that, well, you should prove that each coordinate is continuous. Right? So f is continuous if f1 and f2 are continuous. And f1 here, this is the first coordinate. And this is the second coordinate. So why would that be the case? Well, the story is the same as before. But what I have to do is I have to keep the image points f of x minus f of y, which according to the formula is a two-dimensional object. So I have to keep cosine of x minus cosine of y, and then the other one, which is sine of x minus sine of y. I have to keep these close. I have to keep these close by keeping x and y. Right, so this is a two-dimensional object. X and y, this is a one-dimensional object. By keeping these guys close. Right, so again, how do we measure closeness? Right, so the absolute value of f of x minus f of y, the absolute value, well, it's defined the same way as over here. Right? Just sum up the squares, and take the square root. So this is f, this is cosine. This is cosine of x minus cosine of y squared plus sine of x minus sine of y squared. So if there exists, if there exists a delta, say a delta 1, such that x being less than y, x minus y being less than delta, if that implies that the cosines are close to each other. This is less than epsilon. And if there exists a delta 2, such that x minus y is less than delta 2, if that implies that the sine values are close to each other, then how would I go about creating a delta such that, so what should I choose for delta, such that say f of x minus f of y squared, such that x minus y less than delta implies that, you can put squares here, it doesn't matter, is less than epsilon. What kind of a delta should I choose? If I can prove that cosine is continuous, it means that for any epsilon, so let's call it epsilon 1 bigger than 0, there exists a delta 1 such that if x and y are close to each other, then the points in the image are going to be closer than epsilon 1. For any epsilon 2 bigger than 0, I can find a delta such that I'm going to keep these close, and I'm going to get something here. Now, how should I, so given an epsilon, what should I do? What kind of a delta should I use? What do you guys say? Nobody has a suggestion on how I should, if I can prove, so we have to do that too, and we have to prove that each one of these is continuous. So if I can prove that each one of these is continuous, how do I then get that f is continuous? Well, I get that f is continuous by keeping these values here close. Okay, so I need to measure what does it mean to be close in R2. Well, I need a norm. I need to measure length in R2. And the way that I do it is I take each coordinate and I square it, add them up, take the square root. Right, so this square here, if you don't want to, if it's the square here that's bothering you, we can put it over here. It's just such a messy expression. And so this is, I would ultimately have to prove that sine and cosine are continuous. So I have to establish this. But given that I can establish this, how would I then go about finishing it? Well, if I can keep these ones here close, so say I pick my delta, to be, should I take the min, the max, should I add them, what should I do? Take the max. So now be careful, right? Because if I take the max, just because normally we want delta to be small here. We don't like delta to be big. So we should always do the min. If I take the min here, then if I'm looking at, so fix x, so I'm looking at y's that are close to x in the sense that it's less than delta, well, then both of these will be satisfied. Both of these will be satisfied. Whereas if I took the max, I will not have both of them be satisfied. But if I take the min, both of them will be satisfied. Okay, so then what do we get here? So what do we get here? So I use the formula. Like, so this is going to be bounded by what? Epsilon 1 squared plus epsilon 2 squared. And then you have a square root. But this is arbitrarily small. This is arbitrarily small. This is arbitrarily small, right? Because the statement is over here that by squeezing delta 1 and delta 2 towards 0, I can get these inequalities here to work for anything. Any epsilon you want, I can make it happen over here. So I can make this thing here arbitrarily small. In particular, I can make this thing here smaller than some given epsilon. This is arbitrarily small because epsilon 1 and epsilon 2, they are positive, they are arbitrary. But you see, if I want to have a two-dimensional object to be continuous, what I need to do is to have each coordinate be continuous. And by doing that, by controlling each coordinate, I can control the norm or the length of this two-dimensional object. So what remains here is to prove that sine and cosine are continuous. So it remains to prove this. but sine and cosine here. So sine and cosine, I think it was Priya that said yesterday, I don't just want to look at a picture. And so sine, cosine, and sine, they are much more than continuous. Like the differentiable, in particular, we know that the differentiable, they have a uniform, uniformly bounded derivative. This is what we proved. This is what we use on Wednesday to show that so this here is going to give them that the ellipsis functions. The differentiable, they have a lot more properties than just continuity. But if I understood Priya correctly yesterday, what she wanted was a proof that is basic for why are these functions continuous. So here's a basic argument. So basic proof of why, say, I took sine is continuous. And this is going to be continuous for all x. Right now it's a one-dimensional object, it's just one function. So what is it we need to do? Well, let's prove first. Let's consider the point c equal to 0. Let's prove that sine is continuous at 0. So sine x is continuous at x equal to 0 if for any sequence of points, that converge to 0, for any sequence of points that converge to 0, we will have that sine of these points converges to sine at 0, which is 0. So you give me any sequence of points that has a limit 0, what we need to prove is that I can move the limit inside. Okay, so how would one go about doing that? So we're focusing here on the point 0. So let's look at, I know Priya doesn't want a picture, so I'm not going to use the picture to prove it. I'm just going to use the picture to get some intuition for what we could be looking at. Like sine looks like this. Sine looks like this. So if I look at, I need to make these two things close to each other, right? So I look at the absolute value of their difference. This is sine x minus 0, right? This is sine x absolute value. And what I have available is to make xn small, right? Xn for anything that is going to 0, I need to have that this thing converges to 0. So would I have a bound here of sorts? Could I come up with a good bound here? Well, look at the picture. Like this is absolute value, so I need to put the absolute value here on the right-hand side as well. So what kind of a bound could I have? There's something here. If I looked at a straight line here, and I will look at a straight line over here. Right on the pencil line, this is just y equals x. Right, and on the other side, this is y equals minus x. Right, so what I have here, this is xn. Right, so the absolute value of sine of xn, this is bounded by xn. And this thing converges to 0. And therefore, that difference over here is going to go to 0. Does that make sense, guys? So Priya, I'm hoping this is I was thinking about how to prove this, and without using any of these properties we have up here, right? All these nice properties we're used to. So this here proves continuity at 0. So of course we want to have continuity. We want to have continuity everywhere, right? So let's do step 2. So now let's prove that continuity at any point. So what we need to do now is we're going to have that any sequence that converges to C must imply that the limit of sine of xn is equal to sine of C. How would one go about doing that? Well, what I had in mind was just to reuse what we had before. So if I take yn to be that difference, xn minus C, this thing here is now going to go to 0, right? Because xn goes to C, so that difference is going to go to 0. And then I want to reuse what we just had. I want to use that. There's this formula. I want to use that there's this formula for sine and cosine. So if I write sine at a sum, so I have sine of xn here. So sine of xn, this would then be sine of yn plus C. And I can express this, there's a way to express this in terms of, what is it, cosine. This is sine of yn times, is it cosine of C plus sine of C times cosine of yn. Does that look familiar? And so, yeah, this is one of these identities that are out there, right? And now we're in shape, right? Because the y's are going to go to 0. So by step 1, I know that this thing here converges to sine of 0. I know that this one here, when he doesn't depend upon anything, so this is just cosine of C. This one here, I mean, we didn't prove that cosine has the same property, but yeah, this is going to converge to cosine of 0, and then this is going to be sine of C. And then we use the trig identities again, that this is exactly sine of C. So this here would be one way to give a proof that cosine and sine, these are continuous functions. Are there any questions on this? But of course, again, cosine and sine, they have many better properties than just being continuous, like being differentiable and this Lipschitz property that we talked about. So there are lots more properties on these ones. Anyway, so now hopefully I've convinced you that this function here is continuous, right? It goes from the way that I wrote it, it goes from R into R squared. But of course, it only hits the points in the range. And so, so it goes from R, and it takes values on this circle here. There are no values inside and there are no values outside, but it's on the circle. And the next part of the question is, what about f's inverse? Well, then f in the inverse function, well, that's going to go from the circle. That's going to go from the range. I should just write explicitly what the range is. So it's going to go from R2, a subset of R2, where the length is 1, and then it's going to take values it's going to take values over in R, and it's not going to take all the values. It's not going to be invertible on the full axis. You won't be able to do that. The best you can hope for is something like 0 to 2 pi and then open here. Like you will not, just as you will not be able to get 7 and 7 here, you will not be able to have, you won't be able to have that f minus 1 of a point y1, y2. This is not going to be equal to 10. This is too big. You can't do that. Right, so the range here is going to be 0 to 2 pi. Zero to pi. 0 to pi. Oh, I don't think so. But I would be able to have, like if I take, so this here is where I have pi over 2. Right, this angle here, this is pi over 2. This one here would be, this would be pi, right? And then this one here would be 3 pi over 2. Right, and then all the way around, right, you get up to 2 pi. But then when you get to 2 pi, it switches over and becomes 0 again. So you can go beyond pi. You can go down to as close as you want to 2 pi. And so the sticky point here, as usual, when you look for this, like the troublemaker is going to be where you don't have it to be closed. Right? This is a good point because you have closed here, but this one here, this is where the trouble is. And and so the so f inverse is not continuous. And the way to prove that is one way to prove that is to construct two sequences. To construct two sequences, let's call them y1. Right, so the sequence is inside the domain. So it's y is equal to y1, y2, which is going to be in that range of well, it's going to be f of r. And what should we call the other one? It's called the other one maybe y tilde. So there's going to be two components again, y tilde 1, y tilde 2. So I need to put indices somewhere, two sequences. So I'll call these for yn and yn, and then 1n, 2n, 1n, 2n, n down here, n down here. And then we don't write it as belong to, but now it becomes a subset. Right, so construct two sequences, y and y tilde, such that so it's not continuous, and the point, the troublemaker is this one over here with 2 pi. Right? So on the picture, the troublemaker is this one here. This is where trouble is. That point. So this is 1.0. So it's not continuous here. So we're going to construct these two sequences such that yn converges to 1 over 0. And such that yn tilde converges to 1 over 0. Right, so what does it mean to converge in 2D? In R2, it only means that when I compute the distance from y to this point, what does this here mean? It means that the value of yn minus this 1 over 0, right, this goes to 0. Right, and this is equal to, it's easier if you square it. So typically in higher dimensions, you just square it, and then you'll do y y1n minus 1 squared plus y2n minus 0 squared. Right. This sum here is what goes to 0. And likewise, of course, you'll have it for the tilde process, the tilde sequence. For the square, this is equal to, take the first coordinate, this is y 2n tilde minus 1 squared plus y tilde. The first coordinate is number 1, the second one is number 2. Right, so that's what it means to converge, that when I add these things up, they go to 0. So I need to construct such, so I will construct such two sequences, but when I plug them into the inverse function and I compute the limit, I'm not going to get the same. And I should call this x tilde. Okay, then you cannot be, you can't be continuous. Does that make sense? Question. Alex is asking, wouldn't if inverse of 0, 1 0, 1 0, 1 this point here, this would map to pi over 2. Right, so F inverse F inverse of 1, no, first coordinate being 0, second coordinate, this is pi over 2. Right, and the F inverse of 1 over 0, that's going to be 0. Does this make sense? Are you good now, Alex? Or yes, okay, good. Yeah, so please just interrupt and ask questions here. Right, so how should we create these two sequences, right? Let me try to make a picture again and see if I can visualize it a bit better. So here we have the 1. This is the trouble guy, right? So we're going to have an arc that comes out here. We're going to have an arc that comes down here. And so what we're going to do is, I mean, there are many ways to do this. You don't have to do it the way that I'm doing it, but I'm proposing we start here. This one here, this is going to be my y1. Right, so I'm going to start out at 0 over 1. So exactly that point that Alex wanted. Right, and then I'm going to move out to this point here. This is going to be y2. Then I'm going to move out to this one here. This is going to be y3. 3, and so on. And I'm going to move along this curve here so that I end up here. So I'm going to go in this direction here. I'm going to go counterclockwise on the y's. That's going to come down here. So if I look at f inverse of yn, like, so I could have something like this was pi over 2. So I could have pi over like 2n. Like, so I could start out with the angle being pi over 2, right? And then I could have, we call this for yn here. This angle here, this could be pi over 2n. So where does it go? Well, this thing gets mapped to pi divided by 2n, right? So this converges to 0, right? Which is, like, you're moving along here, the angle gets smaller and smaller and smaller. I'm going to end here. So that was one way to do it. Now the other one, I'm just going to flip it. I'm going to say, well, let's start here now. This is going to be my x1. So this is going to be 0 minus 1. Right, so that's that angle there. That angle here is going to be measured from in here and then all the way around. So that angle is going to be 3 pi over 2. So when I'm looking at f inverse of x, not xn, yn tilde, I should not call them x's because in my notes I call them that. So this is my y tilde 1. This is y tilde n. Well, in general, I want to have the angle. Be like going around. So this will be, the next one will be gosh, can I calculate this? It's almost easier to go the other way around. This would be it'll be 2 pi minus, and then a little chunk here will be minus pi divided by 2n. Yeah. So this was 3 over pi, and then the next one, my y tilde n, this would be 2 pi minus pi over 2n. And now the crucial thing here is that this converges to 2 pi. And so we don't have the right property, right? On one hand it goes to 0, on the other hand it goes to 2 pi. Other questions on what we have here? Right, so on one hand, you have the points traveling down counterclockwise, and on the other hand, the points are traveling clockwise, and they end up at the same place. They end up at, what is it, 3 o'clock in the afternoon. And so both of them converge to the same point, namely 1 over 0. But when you plug them into this inverse function, the inverse function diverges. It doesn't diverge in the sense that it doesn't give you the same values in the limit. Are there any questions on this counterexample here too? Let me say it's a counterexample in the sense that just because the function is continuous, it doesn't mean that the inverse function is continuous. Any questions on it? Okay, so then let's move on to the first part of the question. I mean, so Priya, this is a good question, but the answer is no. You could alter it. You can alter this. You can alter it to say that f goes from 0 to 2 pi, and then it goes into the set of y's in R2 for which absolute value of y is 1. If I alter it like this, then the function is still continuous. Then f is continuous. Well, what now? Is it onto? Is this function, so, and the function is the same, f of x is this cosine x sine x. Is if I change the domain and the codomain around, so like this, would it be continuous? Yes, because it's cosine and sine. Would it be onto? And would it be 1-to-1? Would it be 1-to-1? Right, so it's a continuous bijection. But the inverse is not continuous. So the answer, Priya, is no. So here's a crazy illustration. So the following might seem a bit crazy, but it's not that far out there. It's so here's another way. You can ask this question here. Does there exist a function f? Let me call this thing here something. This is very often called S1. Does there exist an f that goes from 0 to 2 pi over until 1? Does there exist a function f such that f is continuous, f is a bijection, and f inverse is also continuous? I'm sensing this is what Priya is getting at. Does there exist a function that has the properties that Priya is getting at? The one we have here does not work. But does there exist one that does work? So now we're moving a little bit. This is getting a little bit advanced. So do we understand what's going on? So we Priya was asking is it the case that if I would have like this, if I would narrow the domain, would it solve the problem? And the answer is no, it does not solve the problem. But then one could ask a more general question. Would it even be possible to create such a beast so that f is continuous, f is a bijection, and the inverse is also continuous, right? I have this set here, and I have this set here. It's funny you mentioned it, Priya, because when I was an undergraduate student and took a class in topology, where I went to school, we had all exams. And so all exams, the way that it worked at that school was you were just given a question. This here was my question. This was the question you gave me. Is this, can you do this? And yes or no? And the answer is no. And so here is, so why is this not possible? And it's pretty close to what we actually have all the tools to do this. We're almost there. If you take this segment up here, if you take this segment up here, so this is your 2 pi, and this is your 0. And then you have your circle, because that's the circle, right? So that's your circle. This is S1. The way to answer this question, at least at a heuristic level, is that say there is such a thing. Say that the answer is yes. Then what happens is, if I remove a point, now, so remove 1 point from each. Remove 1 point from each. Right? So remove this point here. I'm going to make a hole in it. I'm going to make a hole in this one. So remove 1 point from each. What can you say about this set that has a hole in it and this set that has a hole in it? Well, we have 2 concepts in this class that are these topological invariants. So it's compactness and it's connected. Is this set here compact? Is this set here compact? Very good. Is this set here compact? Very good. So that didn't tell us anything. But here comes the kicker, and this is the thing that is going to go up here. Is this set connected? Is this set connected? So you see there's a difference. There's a difference, Priya. So this one here, I can remove a point and I don't destroy one of the topological invariants. Over here, I destroy it. So it's this property that one can use to get a contradiction. If there is such a bijection that has all these continuity properties, then we know these topological invariants, they're going to remain, they're going to preserve the structure, right? So in particular, it's going to preserve this sort of connectedness. When you map it from here to over here, this thing also has to be connected, but that's not true. So this part here is, I'm not asking you guys to do it, but since it came up, one could ask a question like, is it true that that you can, I mean, maybe there's another function that will do it, but there is not. This is impossible. You can't do it. So while this example here might seem like this is kind of as good as it gets, you will not be able to create a function that has these properties, because there's this ability to remove 1 point in one structure and not in the other, and it starts falling apart with these topological invariants, and this is going to destroy everything. But it was the top part here that this is the most important one, and this was the one that Priya answered. So Priya, are you good on the top part? Okay. Are there more questions on this before we get moving? Okay, so over here on the on problem number 1, I had listed a bunch of things, and I forget who it was. I think it was Aya yesterday that said there was something here with this problem 3. Right? So you have openness, and we talked about this, that when you pull back, you're open. But here, this is where when Priya brought up the example, I was like, this is, yeah, I messed up here. So problem number 3, you can answer this question here. And the answer is, as it's written, it's no, but this is not what I had in mind. So I want to tell you what it was I had in mind. Compactness, right? So compactness, this is when we're talking about topological invariance, right? So when you take a compact set and you push it forward, you get compactness. This is a topological invariant. And the same thing is true with connectedness. Right? There was connectedness on the previous example, like when you took the circle and you moved that one point, it broke down. So when you take a connected set, you push it forward with a continuous function. This is also a yes. But then basically everything else is a no. Right? You can't go in the other direction. Like you can only go forward. With these topological invariants, you cannot go backwards. So let me try to show you some of the answers that I had in mind. Try to show you some of the answers I had in mind. So this is homework 8, number 1. If you were to say stuff like we start out with compactness. So when you push forward, so K compact, then you push forward, you should not expect, so this is compact, but not the other way. And and how would one go about doing that? This was number 5. If you look at f minus f, so f of x be like 1 over 1 plus x squared. X is in R. Then if I pull back, say 0 to 1, I'm going to get R. And this is not compact. This one here is. And the same thing, the other topological invariant is what was that question? That was number 7. If you take A connected, then f of A is connected, but not when I pull it back. But not when I pull it back. And an example could be just a square function. So look at the square function. If I take an interval like I don't know, 1 to infinity, when I pull this back, I'm gonna get something that goes from minus infinity to 1 union 1 to infinity. So I cannot, these topological invariants, they only work in forward direction. They never come in the other direction. Any questions? So these ones here, they're the most important ones. So we're good on that you can push these sets forward, but you can't pull them backwards. Any issues on these ones? Okay, so I want to talk just a little bit about this question that got asked in a way I did not intend. But let's look at number 3. So if A is closed, is the inverse closed? And the way that is, oh, Priya has one. Okay, yeah, I'll do the path connected one. Yeah, I can. is this one here closed? And so what I had in mind was to say yes here, but I mean, this is the way that it's asked is not, that's not the case. So so this is also a no, because if I take a function like f of x is like 1 over x, x being somewhere between, say, 0 and 1, then if I look at f inverse of the positives, but I'm going to get 0 to 1. So this is this is not what I had in mind. So what I had in mind was that the answer should be yes. And what I should have said is we should have been using this. I should have said is f inverse of a closed in O. Now, this is the missing piece. This is the missing piece, right? Because the way that it reads is that it's closed in R. And so what we need to remember, I'll get to use, this will be the last thing we do before we do use. So this subspace topology is what we talked about exactly a week ago. So we need to remember what that is. So recall that for a set A in R, we say that U is open in A if U has the form A intersection with O, where O is open in R. And likewise, we say that V is closed in A if its complement A less than V is open. And we had examples about this topology before, but let me just highlight it one more time with another one. So let's do one more example. If I took A to be like 0 to 1, and then we do union 2 to 3. If I took such a set, then A is open in A. Well, then A is open in A. Right? What does it mean to be open? Well, what do is I take A. Right? So I want to be able to write A in this form, and I can, because I can just take as my open set, I can just take R. Right? So that fits the formula. Then A is open, then the empty set is open. Right? Follow the same recipe. Can I write the empty set? I can. I take A intersection with the empty set. The empty set is another allowable set because it's open in R, but there are many more. For example, another set in this crazy space is that 0 to 1 is open in A. And why is that open? Well, if I take 0 to 1 and I intersect, but I want to be able to write 0 to 1 in this form here. And I can, this is equal to A intersection with, and then I choose another open set in R. What could I choose? I could choose something like minus a half to 3 over 2. So that one is open. And finally, I can also say that 2 to 3 is open in A. Why? Well, because I can take 2 to 3 and I can write it as A intersection with even itself. And 2 to 3 is even open in R, but it's in particular also open in A. Then you can move on to closed sets. If you want to look at some closed sets, well, then we look at the complements. So if I look at V1, this could be 0 to 1. This is closed, right? But it was also open. V1 is closed because if I take A less than this open set here, 2 to 3, I'm going to get exactly 0 to 1. And this set here was open. This is closed in A. And I can do the same thing for the other set, B2. I could call that for 2 to 3. This is closed in A because if I look at A less than the set 0 to 1, right, I'll get exactly 2 to 3. And we argued that this one here was open in A. So in this subspace topology, this is where the question should have been phrased, and then the definition is that F goes from A into R is continuous if the pullback of an open set is open in A for any O open in R. And of course, now we can look at complements. This is completely equivalent to saying that if inverse of U is closed in A for any U closed in R. So that was the one I had in mind, but I didn't write it the right way. So just wanted to cover this thing. Are there any questions on this subspace topology material here? You might wonder, when you see something like this, we're saying that you have openness here. Remember when we started out by doing open sets in R, there were these fundamental properties that those open sets had. When you look at open sets, let me see if I can find it, page 88. Like the properties that we had in a while, when we say unions of arbitrary open sets are open, arbitrary intersections, or no, not arbitrary, intersections of finite collections of open sets, they are again open, right? So we have these properties here for the open sets of R. We should have these properties as well for these for this one that we're looking at here, but we do, right? Because if I take maybe I can write this with red, right? If I take a bunch of open sets, right? So if I take U1 up to U n open in A, well, I want to know that the union is also going to be open. But you can see why it's true, not that the union, this is the intersection, right? This is a finite domain. So if we take the intersection, so take n from 1 to n of un, like I can write out what this is. This is going to be an intersection from 1 to n of A intersection with O n, right? Each of the sets, each of the UN sets comes with their own open set. And then I can manipulate this operation here. I can write this as A intersection with O1, intersection with O2, intersection with On. And then I'll just use the property that what I have here, these are open, right? Because they all open in R, and in R I have the property. This here is open in R. So then the the intersection that I'm looking at has exactly that form that was required for it to be considered open in A. And likewise, I could do the same thing for, I could do exactly the same thing for, if I took an arbitrary, so we call those for U lambda, then what I want to have is an arbitrary union. My tool here is not writing properly. So I take an arbitrary union of U lambdas. What I'll be able to write is each of the sets have the same form as what is listed. So this here would be A intersection O lambda, and then I manipulate the form exactly as before. This is going to be A intersection and then a union of these O lambdas. But again, I know this property here holds. This is open in R. So that union here, arbitrary union, has exactly the same property, as the individual sets do. And so this is a legit topology we're dealing with here. Sets of this form, they create this topology that we call the subspace topology, and it has the same property as the topology on R that we looked at, but it shares different open sets. Like sets like this one here is both open and closed. Sets like this one here is both open and closed, and this is not true in R, but it's true in this subspace topology. So this word in A, this was the thing that was missing from the homework formulation. Any questions on this before we do Priya's path connected one? Any questions before we do the path connected one? So that was down here. 9 or 10. But when you see number 9, this is going to be a no, right? Because you just did that one. We just did that one. Right. We did that one, right? So this one here is path connected. It's an interval. And so when I look at the pullback, it's not going to be path connected. So that one is a no. So the question you're asking about is number 10. Is that correct? Okay. And so the answer here is yes. It is also true that that you can transform a continuous function and stay path connected. I'll try to write out how I would do that. So this is number 10. Number 10, right? So I have A inside O is path connected. Right, I want to prove that f of A is also path connected. And how would one do that? Okay, let's give it a shot. Right, so what do? I take I need to take points X and Y in this range in f of A, the arbitrary. All right, so we need to construct. A path. We need to construct a path inside f of A that connects, that goes from X to Y. So this is a continuous path. So if we imagine here that this is our f of a, where we take 2 points here, and then there's one over here. Like we have to create a path that will take us from x to y. Right, and the entire path has to stay inside the set, this set f of a. Are we good so far? It doesn't just have to be Priya. And what about the rest of you? Does this make sense so far? Alex is good. That's awesome. And what do we have to do it with? Well, I mean, there's not much to. It has to come from the path connectedness of the set A and then the continuity of f. That's how it has to be. There's no way around it. This is where it's going to come from. Right, so the first thing we can do is these x's are inside f of a. So this x here is going to be equal to f of a. And this one here is going to be equal to f of b. But because they live inside the set, so they gotta be, there could be lots of a's and b's that satisfy this, but at least there's one a and there's one b that satisfies this. Right, and a and b are going to be inside a, right? So there exists a and b's inside a, such that when I plug them into f, I get x. When I plug b into f, I get y. And then we use the path connectedness. Then what we have is, then there exists a function p that goes from, say, 0 to 1, and it takes values over inside a, such that p is continuous, and p of, what is it? We started out at 0 to be a, and p of 1 is b. So we have the picture. I don't know how a looks like. This could be our set a. I can go from a to b using a path that I call p. Right, and p takes only its values inside a. So what is the hope then? Well, we need to transform. So then what is the claim? We just compose. I look at f of p of t. We claim that this one here works. Well, first off, where does it take values? So f of p of 0, this is equal to f of a. Right, p of 0 was a, this is f of a, this is my x. F of p of 1, this is f of b, this is my y. I also need to make sure that the path stays inside it here, but it does, because p of t is something that is inside a. This implies that f of p of t belongs to f of a. And then the final one is that p is continuous, f is continuous. That implies that when I compose them, f composed with p is again continuous. How does that sound, Priya? Is that good enough? Could you buy it? It's an interesting thing with, like, so I talked a lot about these topological invariants. So people consider compactness and connectedness as topological invariants, but they do not consider path connectivity as a topological invariance. I've never seen anybody refer to that, but it does satisfy the property. So yeah. Okay, guys, I think this is all I had. Are there any questions or comments? This idea of spending a lecture going over homework, is this a good idea or is it not a good idea? What does anybody have any opinion about that? Should we rather do material than try to redo stuff that that you guys already looked at? I mean, it does slow us down a little bit, but maybe it's worth it. Okay. Alrighty, have a good weekend, guys, and I'll see you on Wednesday.